so just to remind you about the most important information. Very weird. Okay, we have, in a very simplistic way here we're depicting only what we care, for production. Okay, remember that in reality when you drill you actually have a lot of concentric pieces of pipe, casings, that they go from bigger to smaller, smaller and smaller, and they depend on the envelope, pressure envelope that you have to be between the hydraulic pressure and also the fracture pressure. Okay, to avoid that you get the fluids inside the wellbore, but to avoid that you actually frack and break the formation. Okay, that's the reason why you have all of these tubulars. So here I'm just neglecting all of that, and I'm just putting the part that it concerns on production. That is the production casing, that is the innermost casing, and then the tubing. And if we go from bottom up, okay, here we have the reservoir. Okay, if we go from bottom up, first, what do we find? Which element? From reservoir to, to surface. What do we find first? This downhole safety valve. Okay, subsurface safety valve. So we find it here around, maybe 100, 200 meters below the wellhead, and then we continue, and what else do we find? The most important valve in the well, the one that we are supposed to, when we have to go home, we close that valve, and then we make sure there is no leakage to the environment. So that's a master valve, okay? Then we have another master valve that I'm not going to paint for time being. Then I have two lateral valves, which are wing valve, okay? We have master, and then we have, after that, we have the main element. All of these valves, they are on-off, okay? They are either open or closed. But there is one that we use to control production, which is the choke. And that one, depending, it can be a bean choke, something that I change with certain frequency, or it can be an adjustable choke that I can actually control, okay, that I can regulate. And I told you that, something maybe I didn't mention last time. I told you that if you remember, to activate, to keep this valve open, okay, because you have to fight and push a very strong spring to keep it open. So you have to have hydraulic power. And how that hydraulic power enters into the well, actually you have to make a hole, okay? You have to make a hole, okay? And this is what we call this piece of pipe. Okay, this piece of pipe is avoiding fluid to come, this piece of pipe is isolating the space between the tubing and the casing. Okay. Later, if we have time, we talk a bit about architecture. But you have to put here a pipe, okay, a piece of pipe that will bring the hydraulic fluids. Okay, that will be the hydraulic fluids at high pressure. That will have to keep it open. Yeah, and this part here is what we call the tubing hanger. Did you hear about tubing hanger before? No? Okay. But it's actually the part that is making the seal first between the casing and the tubing, and it's also supporting all the weight of the tubing. Okay, the tubing is actually hanged on this piece of pipe, and this piece of pipe is transferring the load to the casing. Okay. Yes, and we'll see how it looks like a bit, if we have time. So this hydraulic line is what we have to have all the time with pressure to keep it open. If something happens, a fire, if you have an electrical failure, what will happen is that's just going to stop, being pressurized, and then you will have that it will close. Okay? And this part particular is called, like a penetrator, okay? That you make a hole in the tubing hanger, to pass things, and you need to sometimes to pass different things. Okay, you have sometimes a pressure gauge, you have a pressure transducer that you want to send up, you have a pump, so you want to transmit power, you have all kind of things that you want to send inside the well, so you do it through this tubing hanger using penetrators. Okay, just a small comment. So those are the main things, and then usually remember, I have two thick, very thick pipes. Okay, that's what I call a header. Okay, and usually I have, because what is the motivation of having a manifold or a header? The first motivation that I told you yesterday? To split the cake, okay? Allocation. Remember that, okay? You have a production header that usually is very big, and you have a test header which usually is smaller. Okay, and then you have to select, because you want to send, this one goes further to production separator, and this one goes further to test separator. Okay, and some countries, like for example Brazil, they demand by law you have to test the well with certain frequency every month or every 2 months. Is by law, you have to report it, and the only allowed method to measure is using test separator, nothing else. No matter if you come and you're genius and say I found the method gives you 100% accuracy, is the same, they don't accept it. Okay, they say you have to have 2 lines, and that's very costly for a onshore system. No big deal, you put 2 pipes, that's all. But for a non-offshore system, it can be extremely expensive. Okay, and for that, remember, we put here first, we don't want to have any surprises that the fluid will come back to the well if the pressure starts to be, so we put a non-return valve or a check valve. Válvula de no retorno is the same in Portuguese? Yeah. Okay, and then we have 2 valves, one that goes to this header, okay, and one that goes to this header. And how do we call these valves? How do we call these valves? These 2? This one and this one? Routing valves, okay? Routing. Routing valves. Yes? So that's the main purpose. That's what we call the production manifold. Okay, this arrangement here, the production manifold. And the main objective is to make test. Okay, it can be for other reasons, but you want to do is test. And when we are onshore, really, we don't have any need usually to do pigging. But when we are subsea, then you want to send a pig, and then the pig has to have, if you send a very small pig and then it comes to a big area, then the fluid will just bypass, right, and it won't flow. Or if you send a very big pig and then it comes into the small area, then it won't be able to pass. It will be, just stuck in place. So you have to make also another sacrifice for subsea systems. You have to make the lines the same size. Okay? And again, extremely expensive. But we have to. Otherwise, wax will start to accumulate on the wall, and then, the system is plugged. Let me know, if you need more time to write or... Okay, so that was the conclusion. We have different architecture. We don't want to go too much into that. You have one thing that I do want to show you is how the Christmas tree looks like. Okay, how the tree looks like for different places. you see very clearly the valves for an onshore. Okay, it's just you have valves and you put them one next to the other attached with bolts. Okay, let me see if I can put it a bit bigger. Okay, and I think you don't have any tree here in the university, no? Because we had one in our place. Okay, when you go offshore, they are actually the same thing, okay, but it's more difficult to recognize. Here, for example, you have a valve. Okay, here you have one. On the other side, you have one. But it's a bit more difficult. It's a kind of a more round structure that has everything. And that's just because of time, okay? When you make each one of these joints, it takes a lot of time. So you try to put everything in one block so you don't have to bolt too much, okay? And then when you go completely subsea, you have a big structure. Okay, maybe that might be 4 by 4 meters, 5 by 5 meters. Okay, and weight a bunch of tons. Okay, maybe I think it's between 50 tons. So it's a massive structure. Okay, and then we came, just the final thing, we came very quickly. We talked about flow equilibrium. Okay, and flow equilibrium, we had basically two things. If we have a system, let's go back to our well again. Okay, we recognize very clearly that we have two boundaries that no matter what, they're going to keep the pressure. Okay, I told you more or less how it works in the separator, and in the reservoir we say at a given point in time we can assume that pressure is constant. Okay, so we say we can actually put a point any place in that system, and we can compute what I call the available pressure at this point and also the required pressure at that point, right? So how the available pressure curve looks like. If we say, for example, here at the wellhead, PWH, okay, versus Q, how does it look like? Okay, going down, yes? If I start producing more and more rate, then the frictional losses in the tubing will be more and more, or the pressure drop in the tubing will be more and more, and then it will start going down. Okay, now, and that one I calculate from here all the way to here. So that curve in black includes IPR, includes tubing. If I have some other thing inside the tubing, like I have a restriction or I have a scaling, something that reduces diameter, I have to include everything in that curve. Everything. So I have to have a model for everything I have there. And then I want to calculate the required pressure from that point to flow against separator pressure. So for that I go to the other point that I know is constant, separator pressure, and I calculate counter current, the required pressure I need to have at that point. And how that curve looks like? Yes, going up. And that curve includes, in this case, P separator, includes the flow line, okay, and any other thing if you have a bend, if you have some losses, if you have some restriction, etc. But the point is that this curve looks from both sides, the point is the same, okay, it's exactly in the same point. So that tells you that if they have to be the same, you have to be operating, that should be the equilibrium rate. Right? Okay. The next thing that I told you is that we are going to focus very much on these 2 weeks on estimate how that curve is going to be, and we are going to look at the cases of gas, cases of liquid, and cases of multiphase, and to see how do we estimate and how do we calculate. Okay, but it's you can use really any tool when you're going to be in the industry. You have, maybe your own routine, you are going to use my spreadsheet, you're going to use a simulator that the company has. But if you have this concept clear in your mind, that's the power. Okay, how you make the calculation, what assumptions you make is not so important. But if you know more or less what to expect, so you can quality control your calculations. I think, to my opinion, that's the most important. Okay, clear? Any question about the homework? No? Remember, you have to deliver, so I suggest you do it, relatively soon. Okay, so far we have seen, so let's continue for today. And today I hope to talk a bit about some different things, but the conversion to standard conditions to local conditions. We are going to see why we need that. How we do that procedure for gas, and that is going to refresh a bit your thermodynamics. All of you took thermodynamics, right? All of you. So you are sharp in entropy. Yeah. Just joking. Okay, and then we are going, if we have time, I hope that we are going to show how that curve or how that equation looks like for dry gas. Okay, and dry gas, you should never, it's very simple. You say, oh, it's only gas, but some of the fields you have here, that equation is a very good approximation. Without using any simulator or anything, you just use that equation. Okay, so never, don't underestimate the dry gas equation. Okay, so first I want to make a comment on equilibrium, is that the selection of the equilibrium point. Okay, and we saw so far two locations. One of them is bottom hole. Okay, and I usually do that to bottom hole. I use if I want to for example, design artificial lift. Okay, and we're going to see what is that. I think Ali is going to cover it, after I'm gone. But basically, you have ESP, electric submersible pump, and gas lift. Okay, in the two options, okay, I put something. In the case of the pump, I put an element here, ESP, a pump, that actually is going to breach. I told you in the choke, right? The case of the choke, that you have to breach that delta P when the available is more than the required. But it can be also the inverse. Okay, it could be also in this area, that the required is more than the available. And then I don't need a choke, but I need something that actually does the opposite of a choke. Okay, in that case I can use an ESP or gas lift that we are not going to discuss here. ESP is just, I have to put a cable, put it down here, and a pump. And then gas lift, okay, I put here a small opening, and then I start to inject. I put a valve here that I call the annular access valve or annular master valve. Okay, and I inject gas through here that will come into the tubing and will start to mix with the oil. Okay, and when it mixes, the density goes down. The density of the oil plus the density of the gas. The gas, I have more amounts, it starts going down, and then that reduces ultimately the delta P. Okay, the pressure drop due to hydrostatic. But I think he's going to cover it later. Okay, design artificial lift, and also if I want to make some, it's like I want to study IPR. Okay. For example, for some reason the productivity of the well went down, and you want to see what might be the cause for that. You are producing less, or you change the completion somehow, so you want to see how that's going to affect your production. So that in those cases you make equilibrium bottom hole. And then I can have also another location that is the wellhead, and that I do for choke design. Okay. I also do it for weld test. Okay. Remember, what I measure usually during the weld test, there are some welds that they have a gauge, you know, down here. There are some welds that have a gauge, so that can give you flowing bottom hole pressure. But most of the welds that you have a gauge here. Okay, so in that case, I use it also for weld test and choke design. But these are the two main locations where I choose to make equilibrium. But you can make it any place in the system. Now that we talk about, choke, okay? So the choke we're going to cover in detail, I think, tomorrow. Yeah, I think that's the day. But let's do, just like a very simple example. Yeah, and assume I have here now a choke. Yeah, and I have very close to it a separator. Okay, and I want to calculate at this point, okay, the pressure downstream the choke. So I'm going to PDC, pressure downstream the choke. Okay. And that's what I'm going to plot the available and required versus Q. Which Q should I use here? Okay, standard conditions. Okay, PDC is going to be seen from the separator side, just like that, right? And now seen from the reservoir side, how does it look like? I didn't tell you yet how do we calculate choke, okay? But you can assume, let's say assume choke is fully open, okay? How does it look like? Fully open choke, I have no pressure loss through the choke. So the curve looks like that, right? Yes? Now let's say I close the choke 30%. Okay, I using that needle, if you remember how was the diagram of a choke. Okay, I just close it. Initially it was fully open. I just close it now 20%. How that curve should look like? Where does it depart? Well, at rate 0, the restriction doesn't do anything. Okay, it should have exactly the same pressure. But then, as I increase the rate, on top of the pressure loss in the formation and the pressure loss in the tubing, I also have a pressure loss in the choke. Okay, so that curve actually should be something like this. Okay, where you have some difference between them that tells you that's the delta P of the choke. Yeah, so that's for 100% opening, and that's for 80% opening. Okay, and so forth. If I go and go, okay, I reduce the WPR because it's another pressure drop. Okay, for now, look at it like that. Okay, I'm just changing the available pressure by closing the opening of the choke. But tomorrow, or maybe I think it's on Thursday, we are going to talk a bit more in detail. Was that clear? Yes? Okay. Okay, so now let's also, I want to discuss a bit about IPR. Because we're going to do some exercise and we require to have IPR. So I want to just to check, that you have the knowledge that you need to that part. Inflow, performance, relationship. And let's go from, now we have a reservoir. Let's assume it's a radial reservoir. Okay, and I have the well exactly in the center. Okay, with RW. Okay, it is so small that I cannot see, and here I have RE, the boundary. Okay, so I'm going to plot. I'm going to see initially everything is closed, so everything is at the same pressure, at the same reservoir pressure. But now I'm going to say I want to plot what happens with pressure along the radius. Okay, and at some point I'm going to say, okay, now I'm going to open the well and start producing and see what happens. Okay, so let's make that plot along the radial direction. Okay, PR, and initially, okay, so let's call this RE and this RW, and initially let's call time equals 0. I have everything is at a constant pressure, that is reservoir pressure, right? The moment I start open the valve, what will happen? Okay, immediately I have a drop. Okay, that pressure will go down because now it's connected to the separator. And let's say that for somehow I managed to keep that pressure constant. Okay, instantaneously in time equal 1, time equal T1 will be extremely sharp. Okay, and all the rest will continue at the same pressure. Okay, extremely sharp. But then with time, what will happen? This has low pressure and this has high pressure, and that causes a migration of fluid from the high pressure to the low pressure. So when that happens, when the fluid moves from this region to this region, the pressure here will drop. Okay, because you have less fluid. So then it will start look something like that. Okay, starting to affect. They don't have too many colors. Okay, until the changes reach the boundary. All of this period before it reaches the boundary, how do we call it? Okay, the pressure, it starts to propagate and it starts to change until I reach, let me paint it in blue, in dark blue. Okay, here it exactly reach the bound. Okay, this blue one that is called T0, T1, 2, 3, T4. Okay, the period between T0 to T4 is called the transient, okay, of the well, or the infinite acting. You heard this word before? No? Okay, the transient, or also called infinite acting. It's like the well feels like it's alone in the world. Okay, I'm the king of the world. It says I'm producing, the pressure is propagating and goes far, far away. My kingdom is, I cannot see it. Okay, that's what happens during that period. But then, pack, I see the bound. Okay, I see the boundary. I start looking at that, and after that happens, then I enter the decline. Then I continue declining. Okay, a similar shape, but to go lower and lower. But I have the same, more or less the same shape. Okay, but just starting to deplete. So when I have in that, let's call it, it's becoming a bit messy, but let's T5 and T6. Okay, from T4 and forward, this is what I call the pseudo steady state. Okay? Yes? Or PSS. That means that the well already feels the bound, okay, has reached, the pressure changes have reached the boundary, okay, and now you're starting depletion. Okay? Of course, anytime, let's say, I put a pump on the well, and that can reduce the pressure, then I will have a transient, an infinite acting period, and then it will enter again into steady state. Okay? That clear? Okay, so the time the time T1 from T4, okay, T0 to T4, is what we call TPSS. So it's the time to pseudo steady state. Okay, depends on many things, but basically depends on the compressibility of the fluid. Okay, the compressibility of the rock. It depends on the properties of the fluid, in particular the viscosity and some other things. But it can take and depends on the permeability. Okay, so for very tight formations, that means very low permeability. Okay, this might take weeks, months, or even years. Okay, so TPSS is in the order of months, years. Okay, months, years. Okay, it's very, very long. And when I have a normal formation, okay, that has a relatively high or medium permeability, TPSS can be just a matter of hours or days. Okay? That clear? Yeah, and you have a formula. I'm not sure if maybe in reservoir you will cover it, but you have a formula to estimate how long that time can, will be. But the point to convey here is that we usually, normally, if we say if the TPSS is short, okay, that means I have a very short time in the matter of hours or days, then I use IPR for pseudo steady state, okay, which makes sense. That means, okay, there will be changes. I will close wells, I will open wells, but this will only take a few hours to some days. But then the majority of the production during years and months is going to be in pseudo steady state. So I don't have to worry about this transient. Okay, I will lose some production. It will be different during that period. Okay, but really most of the production is being done in the pseudo steady state. Yes? So that's why I say in that case I choose IPR for pseudo steady state, or if TPSS is long, then I have to use IPR for transient regime. Okay? And in that case, basically, IPR is a function of time. Okay? I will have different deliverability according to what I have. But we are going to focus in this course. We're going to focus assuming that we are in this regime for this course. Okay? But just be aware that you have two periods. Okay? Transient or infinite acting, a pseudo steady state. These two exist. One of them you have reached the bound, and the other you haven't reached the bound. Still the pressure is propagating all the way to the bound. Okay? To the boundary of the reservoir. That clear? Okay? So now I hope that's what you cover. So let's call PSS IPRs. Okay? So how the IPR looks like for oil, gas, and saturated oil. Okay? That means a mixture of oil plus gas. Okay? The IPR, remember, what does it show? The IPR is PWF, right, versus Q oil in this case. So how does it look like for undersaturated single phase oil? How does it look like? Like a straight line, okay? Okay, and with time, remember that equation, usually it's Q equal to J PR minus PWF, okay? And you found already what J has, okay? How can you estimate J? And that means if PR goes down with time, well, actually, I will have something like that, right? Then how does it look gas? For gas, dry gas, looks curved, okay? PWF, and actually looks something like this, okay, curve, like an available pressure curve. All of them are available, but this one looks a bit closer. And what is the equation that we use for this? If you remember, QG C PR squared minus PWF squared to the power of n, right? You know this equation, okay, the back pressure equation. What is the meaning of n? Or n, what is the range n has to be between? 0.5 to 1. And what does it say? When it's 1, it's Darcy flow, okay, and when it's 0.5 is high, is turbulent flow. That you have turbulent flow inside the pores, okay? It's high velocity regime. So this is the equation, and remember, this is usually for low pressure. For high pressure, for medium to high pressure, you have to use another equation that instead of using pressure, you have to use M, the M function, the pseudo pressure function. Did you cover that also? Yeah, did you cover that also? No? The pseudo pressure function, where M of P is equal to 2 times the integral from P1 to P ambient, to P the standard conditions, from 0 to P of P over me C dP. Okay? Did you see this equation before? Okay? But just be aware that this equation is for relatively low pressure. Okay? I think it's something between 100 and something bar. Okay? But after that, if it goes above that, you have to substitute, instead of using P squared, you have to use the M function, and actually it's an integral that I have to compute knowing the properties of the fluid. Okay, the set, and that we're going to look today, how can you compute set, and the viscosity. Okay, and if we have time, we're going to talk a bit more about that. But just, be careful with that. And N, this is Darcy flow, that basically is like laminar, and this is turbulent flow in the porous medium. Okay, and then how does it look like for saturated oil? Okay, it looks very much like gas. Okay, looks very much like gas. This is what I guess you covered also, Vogel equation. Yeah. Okay, how Vogel equation looks like? QO over QO max equal to 1 minus times PWF over PR, and then plus or minus? Yes? Okay, Vogel equation. Just keep in mind that's, and we are going to work very much in this course in the problems that have with multiphase, we're going to use this equation, and the problems that we have gas, we're going to use that equation, but be careful, remember where it applies, okay, which range it applies. Yes, okay, so that's all I wanted to say for IPR. Infinite acting, pseudo steady state, we are going to use only expressions for pseudo steady state. But maybe you will have, in your professional life, you will see formation that they are very tight. And in that case, you cannot use any more pseudo steady state, but you have to use a transient IPR. There was a question? Yeah?
Yes, I have a question. Because of question for gas. Which pressure we will use as a barrier to separate from low to high pressure? Choose which equation to use.
Yeah, this is in, if you have, like we can find it very quickly for. Okay, that pressure is for less than 100 bar, that equation. Then this equation is for greater than 250, and for the range in between you use that expression. Okay, so it's around 100 bar. For low pressure, P below 100 bar. Okay, after you have to use something a bit more complicated. But this one is valid for the whole pressure range. Okay? Okay, now that that's clear, we have the background also that we need. We have to, start building up some pieces to start doing our exercise on equilibrium. Okay, so I'm sorry it's taking some time, but I just want to make sure we have all the pieces, so when we put them together, there is no confusion. Okay, so that's the intention. Okay, so now let's talk about, if let's say we have again our well, that's why I hope by the end you can do it even if you are asleep. Do you get penalty by your professor because you have bad handwriting or not? I got it in my time. The professor refused to read your exam. Actually, I had a friend that he failed. Not the exam was brilliant, but it was all written in this Egyptian hieroglyphs. So the professor refused to try to read it. Okay, so I will put here in this part. Okay, I'm going to put an engineer. Okay, and I'm going to ask how much is passing through the pipe. Okay, so first we are going to try with one mechanical engineer. How is the mechanical engineer going to report how much is passing through the pipe? Well, I'm a mechanical engineer, so I will say so many kilogram per second, right? We would like to work with mass flow. Yes? So if that's the case, this is going to get fired. Okay? Petroleum, they don't like kilogram. What is that? Mass flow, we don't like this unit, fire. Then I come and bring another engineer, and this guy is a chemical engineer. Okay? And what is the chemical engineer going to give to the manager? It's going to give moles, right? Number of moles, kilomoles per second. That means molar flow. And you know what is the relationship between mole and mass? N is equal to m divided by molecular weight, right? Of the substance. That guy is also going to get fired. Petroleum engineer, even worse. What is this mole that this guy? Just take him away. We don't want this guy. Then comes finally one of you is going to report the rate also on that point. And what is he going to say? This guy, petroleum engineer. Or mechanical but transform, okay? He's going to say standard cubic meter per day, or standard cubic feet per day, or standard barrel per day. Okay? That means a standard condition rate. Yes? Okay? And we will see all of them are equivalent. You know, there must be no magically transformation of mass. Okay? All of them have to be equivalent. So you have to think, you know, in your mind to say all of them are really the same. They represent the same. The only thing working with that, you know, why do we work with standard conditions rate? Because that's what we sell, okay? When we have here come to the separator, at the end we're going to take that oil and that gas and we are going to sell it. So that's why the manager likes it. He comes right with this value that I gave, and he just multiply by 50 barrels, so $50 per barrel, $40, and he already gets the revenue. If this guy gives kilomole, he has to call, you know, some consultant or someone to make the transformation for him. Okay, so that gives you already the feeling how much we are making. Okay. So to talk about that, and let's do it for gas. I'm not sure if you had already the demonstration before, but let's, you know, repeat it just for the sake. Okay. Now let's take so to see how do we estimate this rate. Okay. So let's look at the gas. Okay, at the case of dry gas. Okay. And why, remember this number is very convenient to calculate revenue, to calculate how much the water is producing. But it's not convenient if you remember to calculate friction losses, okay? Delta P due to friction. This is a function of the velocity that you have in the pipe, right? The V, if we see the pipe from the cross section, okay, that velocity that we have in the pipe. And so it depends on the Q, not at standard conditions, but at local conditions. Okay? So it's like an inconsistency that we are all the time working with the wells with standard conditions, but then to calculate pressure drop, we need the real velocity, the local conditions. So we have to find a way to transform very quickly between the two. Okay? So let's talk a bit about dry gas. What is the equation, okay, that we can use? Usually, gases, we can use one equation that works very well. Okay, and which equation is that? The ideal gas law. Okay, starting with that. And what does it say? P V equals nRT, right? Okay, good. And that was a development. Okay, so who was the first one that came up with started to do some observations about that lead to this equation? If you remember I think it's taught in kindergarten or primary school. Okay, Charles, we have some name, Charles, but first we had a guy called Boyle, right? He was the first guy, but actually there is some suspicion that actually he had a colleague, or he was actually the guy that was building his experiments, called Hooke, okay, the one with the spring of Hooke law. So he was building the experiments, the air pump for Boyle, and actually they think that it was him that made the observation, but Boyle just maybe took the credit somehow. Okay, that never confirmed, but they say Hooke is like the Da Vinci of the British. Okay, they want to have their own Da Vinci, so they say Hooke is our Da Vinci. Okay, so I'm going to put you some faces here, so they give you nightmares when you go to sleep. Okay, that was Hooke. Looks like a very serious guy. Okay, he doesn't smile, but that's why he was all pure work. And you have Boyle, that he looked like a very classy guy. Then you had the one that you mentioned was Charles, so that's Hooke. This is Boyle, Charles, Okay, this guy looks a bit more friendly, only partially, right? Then we had who else? Gay-Lussac, that name, okay? Gay-Lussac. Then it's becoming a bit more, terrifying until we reach the last guy that actually gave some more shape to this real gas equation, and that guy is this guy, scary, Avogadro, yeah, that's more or less the timeline. Okay, and that's why you get nightmares. Okay, this guy and the other guy, they're going to keep an eye to see that you're really checking the notes and don't sleep in class. Okay, I have to put someone there to keep an eye, to check what I'm doing. But really, what people start looking is, okay, I have this general equation, okay, and I start to use in any substance that we have. Okay? But actually what people saw is that there was a deviation between the volume predicted by this equation and the actual volume measured. Okay? And that deviation could go between 0.7 all the way to 2. Okay? A relatively big deviation of that equation. So they started to plot for each substance. Okay, so what they did first, they say, we're going now to put a correcting factor. Okay, insert a correcting factor. In the ideal gas equation. Okay, that's what we call Z, okay, C, nRT, okay, and then they started to say, so now let's try to map how the C goes with pressure, okay, and initially at a very low pressure, at standard conditions, okay, ambient conditions, this Z was actually 1, okay, but then when they start increasing the pressure, this was for a constant temperature, it goes down and it starts going up, temperature 1, and the same thing down and up with temperature 2, down and up, temperature 0, and maybe even also started to go and mix in between, temperature 4. Okay, but they could not really find, they had to do that for every substance, so that was very tedious. And we want to have one general equation, not start measuring and calculating all of these C's for every substance. That would be very time consuming. You need a lot of tables, you need a lot of testing, etc. So really the brilliant person here, who came then and found the solution? No, and that one I don't have a picture, just so no more nightmares. So van der Waals, yes, that he came with the concept that say the corresponding states principle, yes. And this guy said, if we, instead of making the plot of Z, if we make it instead of pressure, if we find some variable that essentially is pressure, but resembles pressure, so it's not exactly pressure, but is indirectly is pressure, everything should collapse to the same curve, okay, for all substances. And what is that? What is that variable? What we call the pseudo-reduced pressure okay, PR equal to P over the critical pressure of the mixture. Okay, remember critical is the point where I stop having a clear boundary between gas and liquid. Okay, I just have after that point. And pseudo-reduced temperature. Okay, TR equal to T over TC. Now a bit careful, what unit should we use here? You can use any unit you want, PSI, but the important is that both have to be in the same unit, right? But what unit do I have to use here? Absolute, okay? Absolute unit. So either Kelvin or Rankine, but nothing else. Okay, here is only use absolute units only. Okay, so either Kelvin, Rankine, but nothing else. And after he did that, actually he saw that now if I plot Z versus for each substance, instead of pressure, a variable that is basically pressure, but is a pseudo-reduced pressure. Okay, so each gas will have its own PC and it will have its own PR. Okay, so it does actually exactly the same, has the same behavior, but now all of them for all substances fall on top of each other. Okay, and then I have voila, I have one chart, general chart that I can use for every substance. Okay, I measure it for one and then I can use for everything else. Okay, and these curves are of TR constant. Okay, and then I have a solution. Then I have an equation that captures the deviation from ideal gas and that I can use for my purpose. Okay, so let me show you how that plot looks like. And you don't actually, here in class we are not going to here. Okay, that graph, I guess you have seen it before. Yes, so you see here at the top, how do we read it? Okay, let's say I have 3 of pseudo-reduced pressure and then I have a temperature of 1.4. Okay, pseudo-reduced temperature. So I go 3, 1.4, and then I read the Z, which is around 0.7. That clear? Yes? But now what happens if I have 12 and also 1.4? 12 PR, not reservoir pressure, okay, pseudo-reduced pressure. 12 and TR equal 1.4. If you see, you have 2, because here it starts getting very messy. Okay, after 8, you start getting, all the lines start to cross, and then it's very difficult to see which is for each temperature. So what they did, something very smart in this graph, they put one part at the top for low range of pseudo-reduced pressures and one part at the bottom for high range of pseudo-reduced pressures. Okay, so if I have 12, I come to this plot, then I read 1.4, and I will get a C of 0.4. Yes? Now, one last thing we need to use this plot. So, okay, the way we're going to work is, usually you don't have one thing and then we have to go to Excel. But we usually in production we use not with one unique pure gas, okay, not methane nor ethane nor propane. We work with a mixture of gases, right? So we have, if you see the composition of the gas, so our production gas is usually a mixture of several gases. Okay, and between those gases you might have methane, ethane, propane, butane, pentane. You can even you have some C7 plus. Okay, but you also might have nitrogen. You might also have CO2, carbon dioxide. What else? Is H2S. Okay, that we don't like, but we have a mixture of all of them. And then becomes a problem because I don't really have, each mixture will be different. And how usually how we say which components does that gas has? We use which parameter? The mole fraction, okay? Yes? And here I'm going to call it YI. So say, for example, C1 I have 0.8, that means I have 80%, C2 I have, for example, 10%, C3 I have 3%, and so forth. Okay, and all of them should add up to 1. Okay, that's the mole fraction. Okay, that means from all the moles I have, if I have 1,000 moles, then I have 800 of methane, and they keep the same ratio, the same reference. Okay. So one thing, how do I calculate one thing that I need in this equation, right? Is you will see now, but we need the molecular weight. Okay, so how do we calculate the molecular weight of this mixture? Okay, molecular weight of the mixture. That is something that we need. Is the sum from I equal to 1 to the number of components. Okay, this is what I call components. Yes, of yi mwi. Yes, so I make a weighted sum of the molecular weight of each gas. Yes, but actually that's not what is used. Okay, typically what I use is something else. It's called also the specific gravity of the gas. Okay, and what is that? What letter do I use for that variable? Gamma, yes, gas, or SG gas. But usually in ESPE, the Society of Petroleum Engineers, we try to use always a capital a letter, only a capital letter for a variable, and then the rest I can use as many subscripts as I want, but I have to have only one capital letter. So I prefer to use gamma gas, and then that will be what? Molecular weight of the mixture divided by the molecular weight of air. Okay, and the air is 28.97. Okay. Yes, you have to check if that's correct. Okay, so now we have all the elements. First, we have the Z that we know if we calculate the reduced pressure and temperature. We have the real gas equation that looks like that we can calculate properties of our gas, and we have the final element that if usually the gas is not only a pure component, but it's a mixture of different components. So, but it's very easy. I can just calculate So another thing that is also done is how do I calculate the critical pressure of the mixture and the critical temperature of the mixture? Okay, that's something that I need, right? To calculate the reduced pressure and the reduced temperature. Exactly using the same method that I use for the molecular weight. Okay? You saw this before, right? Some other course? Maybe some years ago? Huh? Reservoir, okay. Yes, so YI, PCI, and okay, we are not exactly on reservoir. We need some of the tools from reservoir. Okay, but to make your life simple, so instead of giving you the mixture and so I'm going to say PC. I'm going to give you a correlation. Okay, a function that was published. I think the guy is called Sutton correlation, and that is just a function of gamma gas, and P and TC of the mixture is just a function of gamma gas. Okay, just to make your life simple. But if you have each component and if you have the mole fraction, then you can just do the calculation yourself. But now to make your life simple in class, we're going to use a correlation that a guy came and said, okay, for the mixture I will do it just based on the specific gravity of the gas. Yes? Okay, so I suggest we take a break, okay? Let's say 15-20 minutes, and then we come back and continue and jump right into Excel, okay? Start just doing things in Excel. Okay, before we go to the Excel file, let's do a let's assume we have any place in the tubing. We have our tubing, okay, and we take a square, okay, just like if we did it at in the reservoir. We take a square with certain amount of gas, N, at a certain pressure and at a certain temperature, okay, P1, T1, okay, and we take that to the surface, to standard conditions. Of course, that's going to increase, okay, and now we have a big volume that we call V as standard conditions, okay, and T standard conditions, P standard conditions. But we have exactly the same number of moles that you had in one, right? So if we apply, let's apply very quickly the equation of state, PV nRT Z, okay? When we apply in standard conditions, actually remember at low pressure that equation C is very similar to 1, okay? So I can use just the ideal gas equation, TSC, NR, PSC, and BSC, okay? And then you see that BSC is equal to N times, all of these are constants, okay? R, what is the value of R? A314.3, right? Joule over kilo mole Kelvin, yes? Okay, so if I substitute those values there, I will get RTSC over PC, and then I get just a constant times the number of moles, okay? For, if you are talking about SI system, is 23.67 standard cubic meter per kilomole, okay? And if you're talking about field units, then we get N times 379.7 standard cubic feet per pound mole, okay? Yes? So that relationship just right there tells you that basically there is a direct, it's just proportional, okay? The number of moles, what this chemical engineer, was fired because he was crazy. He was saying, I'm producing that many number of moles per second. Actually, the same thing as a standard conditions volume, okay? The only thing, I have a multiplier, I have a constant, okay? But it's exactly the same. Yes, okay, so now let's, let's make how many of you have used Excel VBA before? Excel VBA, Visual Basic for Applications? None of you? Okay, but you have used Excel? Yes? Okay. So we are going to go very quickly through a very simple introduction to Excel VBA. It's a very powerful tool. Okay. So you open your Excel. Okay. And then you're going to punch Alt F11, okay, at the same time. Alt F11. And you get this window. All of you got it? Alt F11. Okay, Alt F11 at the same, Alt and then F11. Oh, I don't think I put this one, did I? Yes? You got this window? Yeah? Okay. So this window tells you, it's like the structure of your spreadsheet, okay? All the things that you can find. You have a sheet, you have all kind of things. What we want to have is like, it's like also a programming environment. Okay, when I can make like things like, if you have used MATLAB, I can create functions that they take input, they do something, some calculation, and they give output. Okay, a function is like a black box. Okay, okay, where I have inside the function I have some input coming into the function, okay, and it's just fx that depends on this input and gives you an output, okay, and you can do all kind of things in this function. So that's what we are going to do now, a small test, okay. And for that we are going to say, so we're going to program something very simple. This function, you can write it, you know, in each sheet. If you double click on the sheet, you get this white screen and it says it's ready for you to write something there, to write the function, how to define the function. But I prefer then if you put it there, it will be only available if you work on sheet 1, nowhere else. Okay? So I suggest keeping, like, you have a common repository that every sheet can use. Okay? Any of the sheets, no matter where you are. If I'm here, or if I'm here, or if I'm here, all of them will have access to this function. And for that you have to right click on object, insert module. Okay? And now this module, you see, that's a common place where I can store my functions. Okay? Now to define a function, I place first function declaration. I write on the white space. Okay? And then I put the name of the function, have to have some logical name. So let's call it adding two numbers. Okay? And I have to put the input to the function in parentheses, what that function depends on. So I will say it depends on how many numbers do we want to add? A and B, for example. Okay, and when I click enter, if the syntax was correct, automatically it closes because it's smart. It says you create one function and that function has to finish. And then inside I give the instructions what I want to do with these two numbers that you gave me. Okay, in this case I'm going to do something that's extremely simple, saying adding. Okay, you have to use exactly the same name as the function has, exactly the same. And here I'm going to say, I want to say A plus B, and that's all. Okay, you created your first function. So now let's see and try to see if it works. So we go back to our Excel sheet. You can also do it by pressing Alt F11 to go forth and back. All of you got the module? Yeah, the VBA module? Okay. So you have here on one column I'm going to put A, and on the other column I'm going to put B, and then here I'm going to put the result. Okay? And just to keep clarity, and that's the same convention I have used in the spreadsheets that I gave you, the input I will put in red. Okay? So let's put, for example, 2 and 1. Okay, and I'm going to put them in red. And the results, I usually use the color blue. Okay? The result, here we have to call the function, okay, to make that calculation for us. I can make it very simple, this plus this one, and then I get 3, right? No big thing on that. But when the equation becomes more and more complex, more and more complicated, you are going to make mistakes. Okay? If you start writing square root, division, and then some other things, this divided by that, logarithm, you're going to make a mistake. Okay, it's a very small space, and if you do it multiple times, you will have multiple places that you have to fix. So for that, I recommend every time you have a very complex calculation, use a function, because then you fix it only one place, and then that's going to be fixed everywhere in the sheet. Okay? So let's call it, we use this fx that we have here on the left. Okay? And then we go to user defined functions that I have defined, that I have created. Okay? And those are the ones that we're going to use in this course. Adding. Okay? And then you see it's going to ask me, this function depends on these two arguments. Okay? So I have to say A, and I have to say B, and it gives me the result here, 3. Okay? Clear? To access the function, you click on the cell, press Fx, user define, and double click on the function that you want. Okay? Extremely simple. So, it's why we use Excel. Excel is very graphic. You can make plotting, you can know where your data is, what you're doing with your data. And also when you have this VBA module, it's a very powerful programming language, okay? That you can do many things with it. Not only function, but you can write routines, you can do all kind of things. And also, usually it's available in the company. There are very few companies don't have Excel. All the big ones, they have Excel, okay? So it's a tool that you don't have to ask. If you want to do something, you don't have to ask that they install MATLAB, Java. You just go and do it in Excel, okay? So I recommend, we're going to get a taste in this course, but I recommend it's a very interesting tool.
Professor?
Okay. Yeah?
Why do we have 6 while we are adding 2 numbers? 2 and 1?
Oh, because, okay. Yeah, that's good. Very good quality control. Okay, so now let's go and open one of the sheets that I gave you, called, I think the name was, C factor standing. Okay, this complicated chart that I showed you before, you don't have to go manually and read the values from it. You can use this utility to make it. Okay, and if you go exactly do the same after it opens, you go Alt F11. Okay, you see a function, okay, but a very complicated function. It has a lot of things inside. So first say, what does it depend on? Depends on the pressure for which you want to calculate the C factor, the temperature for which you want to calculate the C factor, the specific gravity of the gas, okay, and the unit, okay, that you want to use. If the input is in PSI and Fahrenheit, then that will be number 1, okay, field units. Or if the input is in bar and is in Celsius, then you are going to use 2, which is metric. Okay? So I have made it here already for you exactly the same. I say put the 4 inputs, pressure, temperature, specific gravity, and units, and C is just calling the function. Okay? So you can, for example, let's say just verify. We have here is SI, okay, so it's in bar. So we are saying all the time that at 1 bar, okay, and ambient temperature, let's say 15.56, the C should be very, very close to 1, okay, 0.0997. If we go at reservoir conditions, let's say a reservoir that has 300 bar, okay, and what temperature do we put? 100, for example, okay, then you have some deviation, like 4%, okay. If we go for a very high pressure, some reservoirs in the North Sea, they can have up to 1000 bar, 800 bar, okay, then you see the deviations start becoming bigger and bigger. Okay, so you have that tool, but we are not really going to use, you're going to use is the other tool that I gave you, but keep that in mind. That's, to introduce the user-defined function, and it has a very complicated procedure to give you set, okay, to give you C. So now let's talk about going back to the, okay, sometimes, if you want to open that, sometimes by default, the security of your Excel is very high, so it doesn't allow to run any code. It deactivates everything by default, okay? Maybe thinks Milan is a bad guy, is trying to attack your computer, okay? And you're going to say, no, this guy, I know him. He's, not so bad guy, okay? So you go here to File, Options. Then you go to Trust Center to the left, in case that happens to you. Trust Center Settings. Macro settings, okay, and enable all macros, just to be sure that you will have access to this Excel VBA that I give you. Okay, sometimes it might happen. You have another company. You are in you have another computer. You are using the company of the computer of the company. So that might be enabled. So that is in options, trust center, options, trust center options, and then macro settings. Okay, and usually what I use, at least when I'm teaching and I'm using these Excel sheets, I say enable all. Okay, and then you are sure your computer is not blocking the access to these functions. Okay. Okay, so now let's go back to the, to that process that we have. We have a volume, okay, at local conditions, volume at P and T, okay, that has some amount of gas, okay, with gas we want to use red, and that one then through the production system, okay, that's at any point in the production system, and that when I bring two standard conditions, okay, to the volume in standard condition. Of course, it's going to be bigger. So volume at standard conditions, at P standard conditions, and T standard conditions. Okay, so I can define. I want to have an easy way, instead of going and looking at the equation of state, I want to have an easy way to relate these two volumes, okay? The volume at one particular pressure and temperature, and the volume at standard conditions. Okay, remember, we are working, usually all of our volumes, all of our rates are using this reference, but we need these volumes to calculate things like velocity, things like friction, things like pressure drop. Okay? And I want to avoid, going and using the equation of state. So what I'm going to say, I'm going to define a ratio that I call, how do I call this ratio? Volume factor, okay, gas volume factor. Okay, if T is equal to T of the reservoir and P is equal to P of the reservoir, how do I call that? Gas formation volume factor, right? Gas formation volume factor. Okay, and how do I define this volume factor? Is the volume at that pressure and temperature, at any particular pressure and temperature. Okay, not only at reservoir and temperature, but at any. That's extremely important for us, for production engineers. We want to know at any point in the system. Pressure can change wildly. From reservoir pressure can have really any value, and temperature also. So we want to have volume at any pressure and temperature divided by standard condition volume. Okay, and we have, of course, we have the expression how that looks like for, with using the real equation of state. That looks C N RT divided by P, right? And here we have N C R T standard conditions and P standard conditions. Okay, this C is actually not C, but is 1. Very close. This one cancel each other, and then this one cancel each other, and what do I get at the end? C T PSC over TCS over P. Yes? Okay, and that's how, so if I give you, the rate that the gas, this bar on top indicates that it's at standard conditions. Okay, the bar is a convention that we use normally. So the bar on top is at standard conditions. If I give you that number and I tell you find QG, okay, at P and T, so what is the procedure in that case? So I say QG at P and T is equal to BG at P and T times Q at standard conditions. Okay? So it's very simple. It's just a multiplier that I use. And that BG usually, should it be greater than 1 or less than 1? Remember the definition, okay? What I have locally, what I have in the surface. In the surface, it becomes extremely high volume. That means that this one is much, much bigger usually than this one. Okay, so it's a value much, much smaller than 1. Yes? Okay, but you see it's just a multiplier. So every time I need a local rate to calculate velocities, I have to use this factor. Okay, and this factor, if it's for a dry gas, that means that when I bring it to surface, doesn't have any liquid, then it's just this definition holds. Okay, it's exact. And here, just now that I mention it, here we're going to make a clarification. When I bring it to the surface, this comes no liquid is condensed. Okay, and that's what I call here BG dry. Okay, that means that there was no condensation of liquid from the gas. And as you can imagine, really that's not always the case. Okay, sometimes, or in many times, when I bring the gas from local to standard conditions, actually I will have some liquid. I will have some liquid coming out. Okay? But what I'm going to take is only the volume of the gas. Okay? In that case, the BG is called BG wet. Okay? Wet. But just keep that in mind. When it comes up, it might have some liquid and I neglect it. Okay? And that's the difference between the two. But for this case, we're going to use just this one. Yes. Okay, so let's see how, using now the other spreadsheet that I gave you, and that's going to be part of your homework that you have to deliver. So we want to see what will be the BG, the behavior of BG versus P. Okay? And let's say here we're going to go from separator pressure. And let's say separator pressure is 35 bar. All the way to reservoir pressure, that is, let's say, 300 bar. Okay, let's see how that plot looks like. Okay, so I recommend for that you go to, so you see, to calculate BG, we need the temperature, we need pressure, we need this is a constant, okay, and we need this nice function that I already gave you, okay, the C factor of Stadman. So let's open the other file. I have to close this. I gave you one file called BG dry gas. Okay, so open that file. Okay, and here you have I have added one more column. Okay, called BG. Okay, and BG depends on, if you see, click here, it depends exactly on what we need: pressure, temperature, deviation factor, and unit. Yes? And we can go back, Alt F11, and see what is the definition of B, just to see that Milan didn't make any mistake. Okay, and again, if I have unit 1, that means field, and that means I have to use the PSI, and I have to use Fahrenheit, or if not, I have to use bar and Kelvin. Okay? And here it tells you what units you have to use: PSI, C, and Z. So what I suggest on that plot, let's make, okay, so let's calculate BG. Let's use a specific gravity of 0.55. Okay, specific gravity of 0.55 and a temperature of let's use 80 Celsius. Okay, and let's see how that plot looks like. So I suggest, starting here, we set 300, was it? Reservoir. The temperature was 80. This was 0.55. Okay, and I'm going to use in field units. And that's the BG. Okay, that's the upper bound, the reservoir pressure. And then I want to go down. Let's see, let's make it every 20 bar. Okay. So we say this one is the previous, you have to do it with me, otherwise, well, you can just watch me, but then you will have problems doing the exercise later. Because the exercise is based on this class exercise. Okay, 280, we drag it down, okay, all the way to when we reach close to 35, and here we put 35. The temperature, we say, will be constant. Gravity, that doesn't change. Okay, it's the same gas that is just passing through different pressures. And the units that I'm going to use is SI for all of them. Now I drag the C factor. Okay, we'll have some variation, not much, and then the BG. Okay. Yes, you saw how I applied the equation. I just pull it down, and then the equation, it says, well, here I'm taking this cell B, D, and E, okay? But when I drag it down, automatically Excel is smart and say, okay, now I have to use the ones below, exactly at the same row that the other ones that I'm using. Okay, so now let's plot that to see how it looks like. Okay, and I get a bunch of things that I don't need. Okay, pressure, that's the x-axis. Okay, when you deliver your homework, okay, some basic things. The plot has to be in a different sheet. Okay, so here I have to put the plot BG versus P. Okay, then the font usually by default is very, very small, so I recommend to increase it, and usually what I like to use is 16. Okay. Now I use also bold, and you have to put also the titles of the axis, and for the titles come here, and I say this one, and the way I say is gas, volume, first the name of the variable, factor, BG, and then the units. Okay, and in our case we are using, what are the units of BG? It's a volume at local conditions divided by a volume at standard conditions. Okay, so I suggest using cubic meter over standard cubic meter. Yes? Name, symbol or symbol that I'm using, and then units. And here on the Y, pressure, P, and that is in bar. Okay, and by default also usually these lines are a bit too weak, so I use these lines. I use black, and I use also black, and I can make this one also a bit thicker. Not sure why it likes this color, but we can change it. Okay. Yes. Okay. So that's how kind of a proper, good enough plot looks like. Okay, and you see it goes actually from values what we expected, very small, but actually when we increase the pressure, it becomes the local volume is very small, okay, due to the pressure. So when it expands, there is a big change between the two. The ratio is very big. Now when I have closer to the separator pressure, the ratio is not that big, but it still is significant. Okay, so that's how the plot looks like, and here we're going just to put it by hand. Okay, the plot looks like that. And again, if I ask you, if I come in the middle of the night and say, wake you up and say how the BG looks like, you have to know, sleeping, you have to know how it looks like. You have to memorize it, okay? Don't discard it. Maybe I go to one of your houses, to one of your homes and ask you in the middle of the night. Okay, so your homework, it's you're gonna have to repeat the same plot, but for temperatures of 120 and temperatures of 60. Okay, and put all of them in the same plot, with nice formatting, and see and see how it looks like. Because usually we don't have only pressure, but also we have that the temperature will change. Okay, so the two things affect the BG, and that means that I have to take the two into account when I want to calculate local rates. Okay, any question? So that's the homework. Number 2. Okay, you see they are not too demanding, but it's to plot BG. Okay, for these 2-3 temperatures, 80. Okay, and for a pressure between 35 bar all the way to 300 bar, okay, and a specific gravity of 0.55. Okay, and if someone of you wants to try, you can also do it. I accept also you do it in field units, no problem. Okay, if you feel more comfortable with using field units, no problem. Okay, start it start to accumulate, so do them in good time. So far, so good? Yes? Okay. Now let's go to the final part of this class, which is the development. I told you that we are very concerned about, in this course, in these 2 weeks, of this curve, okay? We have the IPR, but we are very much concerned about the TPR to see how it looks like. So now we're going to go, I'm going to try to do it. It's going to take some time, so just bear with me and also correct me because I do mistakes. I have the pressure, all of you watching me, so I have to, but you have to do some quality control. But I'm going to try to develop it from scratch, the gas tubing equation, and then we try and plot it to see how it looks like. Okay? So we start from, so that's the development of the dry gas tubing equation, okay? And this equation also could be used for actually flow lines, okay? Not only, because we will see the tubing is basically a pipe that goes from a point P1 to a point P2, okay, that's the tubing. And that pipe can also be inclined, okay, can have some inclination. Yes? But that in theory, I can use this equation to predict for any flow line that I want, okay, for any flow line. And then you ask me, for example, okay, Milan, you say very interesting, but our wells usually, for example, are like this, and then I have a section like that, and then I have a section like that. So how to deal with that case? What you're going to teach us is for just one inclination. What is the answer? Okay, this famous guy, what was it, Caesar? He said, divide and conquer. Okay, so in that case, you make one equation for this segment, one equation for this segment, and one equation for this segment. Okay, 3 equations, but you use the same equation. Okay, no problem with that. So that's divide and conquer. Okay, so Okay, we have a tubing, okay, flowing from 1 to 2. We have a length, okay, that's going to be the variable called L here. And also we are going to define an angle called alpha. Okay? And usually well bores, that's the, you maybe mechanical engineer, you say, oh, I always define the angle here, but in this case we always define the deviation from vertical. Well bores are usually vertical, and then if I have any deviation, that's the angle that I use. Okay? Also, here say also applicable okay, so we start saying dP, okay, with the simple equation, Bernoulli equation, saying that is equal to density times gravitational acceleration times the h, okay, and the h, how do I express it? By the cosinus of alpha, right? Okay. And this is minus, okay, minus so this is the hydrostatic term. So you say, what happened with the length, okay? I ask you, what happened with the length in this equation? I have density, I have gravity, and then I have an angle, but what happened with length? It's here, okay? I divided everything, both sides of the equation, by length. Okay, so length I have it on the left side. And then I need the velocity, and what is the velocity? The expression for the velocity, friction factor, velocity divided by 2. Okay? Yes, so now the main problem when we are going, okay, so now we have to go from here to here, okay? But the main problem with that is that P changes along the tubing, and also T changes along the tubing. Both of them are changing. So here comes this big problem that that the density, we said already, is a function of pressure and temperature, right? So like we will see, we'll go very quickly through liquid, maybe by Friday, through liquid. But here we have to put actually that dependence. For gas is extremely important. Density and then also velocity, they are affected by the pressure and temperature. So what I suggest, we have already one tool that is very important, that is the real gas equation, and we say that we can represent density by P molecular weight over CRT. Right? Yes or no? Okay? At least that's what I have here, so you have to check. And then I insert that equation here. Okay? I say, well, no problem. I know density will change, but I have here a function of pressure and temperature. So I insert it in this equation. dP dL equals minus PMW over ZRT times G times cosinus minus F P MW over ZRT and U squared over 2 phi. That's the diameter, okay? The inner diameter of the pipe. And then U, what is the expression for U? That's the velocity of the fluid inside the tubing. Okay, so that's the. So let's express it. We say we are going to say really there I should use what petroleum engineers like. They like the rate at standard conditions, right? But let's do it from the mechanical engineer point of view, and we can say that that's a mass flow divided by first the density to give you the volume rate, okay? And then I divide by the area of the cross section of the pipe. Yes? Clear? And then that gives me That's kilogram per second, that's kilogram per cubic meter, and the area is squared, is meter squared. And then I take it away, take this away, and that gives you meter per second. Okay, so it's consistent. And the area is pi phi squared times 0.25. So I substitute that, so that tells you that U is m over times CRT over P mW times P phi squared and 4, right? Okay, so I substitute that in this equation, and I get dP of dL minus, this part stands the same, minus F, and here I can cancel some things, right? Because I have I will have CRT squared, so this will cancel. Let's do it, just complete. And then this one will be actually 4 times 4, that's 16. M squared ZRT squared over P squared and W squared and that I move it to the right. Yes? No, didn't make any mistake, didn't forget anything? No? You're doing the quality control, okay? If the equation at the end, we create a new equation and then we have to publish a paper or something, so just do some real quality control. Okay, we take this one, cancels it with this one, then this one of the pressures cancels with this pressure, one molecular weight with this molecular weight, and these two cancels with 6, and then I get 8, and then at the end I have dP over dL equal to minus PMW ZRT G F over, so here I have phi to the 5 times times P, what else I have here? Molecular weight, okay, and then M squared ZRT 8, okay, good, we have some people checking, that's fine. Okay, so now what I'm going to do to make my life simpler, I'm going to we like to change variables. This equation might be a bit too complex. What I have to do now is to integrate, okay? I have to integrate this equation from point 1 to point 2 to give me the pressure drop. But, like that has too many things and I can make, very easy to make a mistake. So I'm going to create a constant that I define called, let me call it B. Okay, and B will be MW times G cosine of alpha divided by CRT. Yes, and then I create another constant called D, and that D will be F ZRT 8 over also M squared C to the 5 MW. Okay, so I put everything in there except pressure. Pressure I leave out. Okay, but I put everything there except pressure. Okay, so at the end the equation ends up being dP over dL is equal to minus B times P minus D over P squared. No, actually P is not P squared, no, it's just P. Because the P squared got cancelled one with this one. Yes? Looks fine so far? No mistakes? We're not going to find the new equation. Okay. So now comes one. So now I can make, put the snakes on one side and on the other side. Okay. Remember, I have this variable separation technique that I have to put everything that depends on pressure on one side and everything that depends on length on one side, and then I integrate both sides. Okay. So let's do that, and we see dp over and the minus, I keep it here, bp plus d over p and equal to dl, right? Okay. Now to integrate, we have to do something, and we have to make one small assumption that you will see. We have to say to be able to integrate, right? Because the pressure will be changing from 1 to 2. What is the assumption we have to make? The assumption is that B and D are constant, yes, with pressure, okay, or are constant. So I don't have to integrate these two variables. And you see that creates some problem for me, because I say, well, you have this set, okay, and you have also set, and you have also temperature. These two are going to be changing. So what I'm going to say, I will say, well, let's use, instead of using this C and T, I'm going to use not constant with pressure. So I don't like this approximation. So I'm going to say are constant and equal to B equal to MW G cosine of alpha over Z average. Okay, I'm going to calculate at an average. I know it's going to change, but I want to calculate at an average compressibility deviation factor at an average temperature. Okay, an average temperature is defined as T1 plus T2 over 2. Okay, and C average is going to be evaluated at average pressure and at average temperature. Okay, and D, the same thing. D is going to be F, and we will see now something tricky with F. Okay, F we can see now is average, but you will see just now something very interesting happens to F. Z average, RT average, 8m squared over C I m w. Okay, so I make that assumption that B and D are constant because I'm evaluating at an average temperature at an average factor. So after I have that, no problem, I can put the snakes both sides. You also call them snakes? La culebra, no? Serpiente. How do you say snakes in you don't have any snakes in Mozambique? No? Yes, you don't have any snakes in. You have, okay. Poisonous or not? Yes, okay. So you have to make the integral. Okay, from 1 to 2, and I'm going to put just this minus on this side so it won't interfere. And here I just have minus L, right? The length, the linear length, or the length along the pipe. Okay, just the difference, the length of the pipe. And here, to solve this equation might seem a bit complicated, so what I'm going to say, I'm going to change variables, okay? I think here I made a mistake, no? Okay, so here I'm going to reorganize. I'm going to say this integral is going to be P here, dP over B P squared plus D. Okay? Yes? And now we say change variables. And I say that U equal to B P squared plus D, and du equal to 2P B dp. Yes, I think so. Okay, so that integral now can be from 1 to 2, now can be evaluated as d big U. This is not velocity, okay, that's a big U, that's the variable I'm using to integrate, divided by U. And then to make it the same, I have to divide by 2b, right? Yes, to cancel these two things of the du. What is the solution of this equation? Logarithm, natural logarithm of u evaluated in 2 divided by u evaluated in 1. Okay, very easy. It was a complicated integral, I made it very simple. And now I return the change, return the variable change, and that gives to be ln of b p2 plus d and b p1 plus d. Yes? And equal to minus L. So what I'm going to do now, I'm going to take the exponent, I'm going to pass these two to the right, and I'm going to take the exponent of the whole expression, 2b, and that will be e to the power of that, right? And then I just got rid of this, b p2 plus d over d p1 plus d. Okay. Let me check if we are on the right track. Okay, and then I'm going to define that S is going to be, S is the elevation factor that is going to appear later on, but S I'm going to define it as 2L times B. Okay, so this is e to the power of minus S, B P2 squared plus D, B P1 squared plus D. Okay. And then doing some, something that you can do later if you are bored, you need to practice with your mind. So you end up with the following: P1 squared equal to P2 squared e to the S plus B over D ES minus 1. Okay? You end up with that equation, which has almost, so where, we want one equation. What are we looking for? Remember, we are looking for an equation. Okay, no, don't lose the perspective here. Q standard conditions. We are looking for an equation that if we give, what are we giving here? We are calculating from separator all the way to from the wellhead all the way to downhole. Okay? So which one is P1 and which one is P2 in that case? Okay, we have our well. Again, I'm going to draw, this drawing is not going to go away. Yeah, so I'm going from P wellhead all the way down to PWS. Okay, counter current. So I'm looking for an expression. So in this case, P2 is equal to PWH. Okay, P1 is equal to PWF. Okay, and I need something else. I want to plot PWF versus rate. Okay, so I need the rate someplace. And where is the rate in this equation? The rate is here. If you remember, B and D has the mass flow, and the mass flow is basically the standard condition rate. I have to use now this BG that I told you about to convert from mass flow to standard conditions. Okay, so let's look more in detail what B and D is. So V over D equal to I'm going to just copy from here. M squared C average RT average 8 F CRT divided by molecular weight times pi squared phi to the 5 molecular weight the cosine of alpha. So this one, no, these two actually don't cancel, but they are squared. Okay, so that's the expression of this ratio between the two, and that's where I have m. And what I'm going to say is m is just equal to the density at standard conditions, okay, times the rate at standard conditions, right? Okay, let's see if the units make sense. This is kilogram per cubic meter, and this is a cubic meter also divided by any unit, in our case days. Okay, so the units at the end, the units at the end make sense. That gives you in mass flow. Yes, so I'm going to use this expression, and the density at standard conditions we know is equal to, using the real gas equation, we had it here right before. The density, it's okay, this equation here, okay, but now for standard conditions. Okay, so it's P standard conditions over Z, that Z is equal to 1, R and T standard conditions, and we are missing here what? It's the molecular weight. Okay? Okay, and we substitute that here, M in this equation, and at the end we end up with B over D equal to Q standard conditions ZRT average 8 times F okay, the first time you do it, not very easy, but then after you already know where the equation comes from, you can derive it yourself if needed, but what we really want is then to use it, okay, to use it in our case, in our equilibrium. So let's see, that looks okay. Okay, so that's how in this equation that I have almost looks the same what I need. The only thing is that I have to, fabricate the rate somehow, and the rate I just did by converting the mass flow. And then at the end I end up with something like that. P1 plus P1 squared equal to P2 squared e to the s, the elevation factor, plus Q standard conditions times a constant, okay? Times something that has many things inside that we are going to see right away what it is. But what I'm going to say to be consistent, I'm going to say this constant is 1 over Ct squared to be consistent with the Q. It's something that because I want to have at the end an expression that will look like P1 squared P2 squared e to the s plus Q standard conditions over Ct squared. Okay? So I want to have one equation like that. So every constant, and you can make the homework also again if you're bored and need to to practice with your mind. So you can find out exactly what it looks like, but here I'm just going to paste the expression, okay, how the final expression that we have. Okay? That's the equation we are going to use, and that you can use with all confidence for analyzing the tubing performance relationship of dry gas wells. Okay, that I guess you have many of them here in Mozambique, so this can be the working horse for you for the future. This equation. Okay. Yep. Any question? Okay, so we're going to go very quickly. I should let you, you do it yourself. Try to find the units, which parameter I have to use in which unit. But I'm going to make your life easier, and I also gave you a calculator to estimate. So you have to estimate for a given configuration CT, and you have to estimate S. These are the only two things that you have to calculate. Okay, and you have to do it with all this input that you have here. Okay, and for that we're going to use Excel. For that we're going to use a user-defined function that I already made for you, so you don't have to worry about it. So, but there was one thing that was pending. Okay, that this F that is concerning me a bit. Is troubling me a little bit. That what is this friction factor? Okay. Friction factor, again in the same way that we have the set. Okay, if you were plotting delta P versus velocity, people try to make experiments, and they did for different configurations, different geometry of pipe, different diameter, different fluid viscosity, etc., and they never got to the same result. Okay, they got different results for everyone. So it was very inconvenient, because then you had to make a test for each system that you had, for each viscosity, for each density, for each etc. But then came a genius and said, why don't we use the same method that we have used for the C factor, for the deviation factor? We don't have to plot the variable, but we have to plot an adimensional variable and a scaled variable that in essence is delta P, and in essence is velocity, but is like an adimensional variable, and then I will see that all the curves for all systems collapse to the same curve. Okay. So how did he call these two variables? Instead of using velocity, what will you use? Reynolds number. Yes? Rings a bell? Reynolds number, that's defined as velocity times diameter times density divided by viscosity. Okay, and you might say that that's like inertial forces. Okay, velocity forces divided by viscosity forces. But basically, I'm adimensionalizing velocity, and then I have the F, which the definition of F is delta P over B kinematic times phi over L. Okay, a kinematic energy times D over L. Okay, and like that, magically, all the graphs, all the people that did measurements of delta P versus U, with time, all of them collapsed into one plot again. We did exactly the same trick that with the deviation factor, just by finding this magical number. Okay, this magical F and this magical Reynolds. And how the graph looks like? Laminar. First you have one regime that you call laminar, right? And that's up to which number here? Reynolds number? 2,300, okay? Maybe 2,500, okay? Then you have some crazy thing that starts like a transitional zone, okay, that we don't really know exactly what happens there. And then it starts going down again, and that's what I call, so this is the laminar, okay, and that here is the turbulent. Okay, and that curve depends on what? I have a family of curves actually. Okay, go down like that, okay. They depend on what? This, if you remember, all of these different curves. The roughness, okay, of the pipe, the relative roughness, which is basically the roughness, E, which is the roughness, E divided by the diameter. Okay, if you see the pipe in the cross section, really when you make a zoom, actually it's not straight, but it has some roughness. Okay, if you make a zoom here, you will see that actually it's not straight, but you have something like that. Okay, and E is that distance of this small roughness that you have in the pipe. And then what you do, just adimensionalize. A dimension is a very powerful weapon, okay? When I did that, I basically made a general plot that I measure only once and then everyone can use. You don't have to repeat measurements. Also for the deviation, please keep that in mind. Okay, that's what we did. We dimensionalize pressure drop, dimensionalize velocity, and then we have a generic plot. Now we come to the trick for gas. For gas, usually Reynolds number, this viscosity is very, very, very small. This density is also very, 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 very small. But this one is even smaller than this one. Okay? So what happens is that the Reynolds number is usually in this regime for gas. Okay? Of gas flow. Almost always. Always. So in that case, you see, there is no dependence. It's just a constant. Okay? With Reynolds number. Doesn't have any dependence. Yes? Only has one dependence. It depends on the relative roughness. Okay? If I have the relative roughness, I already know the value of the friction factor. Yes? Clear so far? Yeah? So I take away all what we have to do for liquid, that we read the Reynolds number, we go to this graph, the Moody or the Colebrook graph, and then I read the F. I take all of that away from my mind. I forget about it, because gas is always very, very turbulent. I don't have any dependence on the Reynolds number. Okay, sounds very crazy, but that's the beauty of gas. Okay, and then came some researcher or some engineer in very early, I think was in the 50s or something, and then he said that he went to all the places where they manufacture this tubing, okay, one by one, and he tried to make a correlation. He said, okay, usually the pipes of this diameter always have this roughness, okay? So he tried to find the relationship between E as a function of the diameter, okay? Went to this place, where they manufacture different places. And at the end he said, really, you can have one unique, usually, let's say I will get 100 microns if you have a pipe of 2 inch. I will get 300 microns if you have a pipe of 3 inch, and so forth. Okay, found the correlation. And in that sense, so he came up with this equation that says that the friction factor is just 0.0777 divided by d to the power of 0.224. This is for d in meters, okay? But I can give you also for d in inches. And problem solved. Then I can insert that friction factor that depends only on the diameter of the tubing in my previous equation. Finished. Yeah? Okay? Very, sounds simple. The equation, you have a lot of constants that you have to insert, but it's really powerful and it's really realistic. Okay, that really captures the complexity. So now to finish, everything clear so far? Or more or less, but more or less clear? More clear than no clear? Yeah. Okay, so now to finish, I'm going to show you an Excel sheet I made for, it's a bit early, but I think you deserve was some theoretical development here. There is one called tubing constant calculation. Okay, open that one. And you will see this gives you at the end, remember, input in red and calculations in blue. But at the end here I have the S and the CT. Okay, this is the CT. And what do I need for that? I need the height of the tubing, okay, of the section. In this case, I'm assuming a vertical pipe of 3 kilometers, 3,000 meters. Internal diameter, 0.15, that's like around 7 inch, okay, like 6 inch ID. Gas gravity, this is very lean gas, is like methane. Line length is vertical, so it's exactly 3,000. Here, inlet temperature, what is the inlet temperature to the tubing? Reservoir, okay, temperature. Yes, the gas enters at the same temperature as the reservoir. Then outlet temperature. I don't know if I have a gauge, if I have a transducer, I measure and I use it. If not, I maybe assume, okay, let's say 20% reservoir temperature. Inlet pressure, okay, no. If we start producing with the IPR, then we don't have any more reservoir pressure. Okay, this is the tricky part. So if you remember in the IPR, if I have flow, okay, the IPR tells you bottom hole pressure, available bottom hole pressure. So if I'm producing at a certain rate, that's the pressure I will have at the bottom of the tubing. Okay, that PWF. And that's where it comes a bit tricky, that I have to assume a number before I actually have computed that number. Okay, I have to assume. But you will see if you, so we assume these two numbers, that the pressure will be a pressure drop. For example, I can use to start with, I can use reservoir pressure. And this pressure at the top, I have it. Okay, that's part of the calculation. And then I calculate, and I calculate my C, and after I run my computations, I can see if that was a good assumption or not, and eventually change the CT. Yes or not? More or less? Comme ci, comme ça? Mais ou menos? Okay? And also DS is calculated here. So we're not going to go too much into, this is the only place I show you how do you calculate CT. You're going to get an exercise tomorrow. But we are going to, so for the examples we are going to make tomorrow, I'm going to give you the CT and DS, and we are going to perform equilibrium on that. Okay? And there it will be a bit clear that you have to do iteration. So check tubing, constant calculator spreadsheet. Okay, and you're going to have a class exercise tomorrow on that. Okay. So just to summarize, okay, what have we done today? Today we made a brief summary, very brief recap of what we have done yesterday. You saw some pictures how the Christmas tree looks like. Significantly more expensive, much more complicated, much more complex, but that's where it has to be. Then the equilibrium, we select multiple locations. You can select everywhere you want, but there are two main ones. One is at the wellhead and one is at the bottom hole, and I use it for different purposes. The choke, I told you intuitively, we're going to talk about it tomorrow, how to include the choke in our calculations, but you can see that it's an additional pressure drop. So I can just really put it very easily. I say if there is no opening, I get this curve here, and if it's closed, then it starts affecting and reducing, actually like scaling my available pressure curve. Okay, intuitively, but you will see later tomorrow what happens. IPR, a quick refreshment saying there are two types of regimes in a well. Okay, the infinite acting, the transient, when the well feels like it's the king of the world, I have nothing around, I can do what I want, and then bang, the boundary happens. That's a pseudo steady state. Usually the IPRs that we use are for pseudo steady state, and this is how they look like for oil, gas, and saturated. We're going to use actually this equation in the example tomorrow. Okay, then the relationship between mass flow, molar flow, and standard condition rate basically is the same. Standard condition rate is very practical. Okay, I can already relate it with gain. Okay, with economical gain. But it's basically the same. Gas is very nice that we can use the real equation of state, okay? And we have a nice calculator that we can use for that. And the practical way, instead of using the equation, I use one factor called BG, okay? That relates always the volume at a certain local conditions of P and T with a standard condition volume, okay? It's a ratio between these two. And I give you a tool that you can use to calculate. And actually, maybe this factor is what we use in the tubing equation. And so you have homework is to make that plot for different temperatures. not it's not a big puzzle. It should be done quickly. And then we went to the derivation of the tubing, and this equation is valid for constant diameter and constant inclination. If your well has some differences, then you have to split it into sections and create CT and S for each section. Okay, so we went deriving from the equation we know, Bernoulli equation, and some mathematical tricks, etc. And we reach with that equation, and we haven't plotted it yet to see how it looks like, but we suspect it's going to look something like that. Okay, that's what we expect, and let's see tomorrow if that's how it looks like. Something interesting for gas, the friction factor depends only on the diameter of the pipe. Finish. No more, no other things. Okay? Questions before we finish? No? Okay, tomorrow. Bye bye.